go on here. All right. So this time we'll look at a rare disease, even more rare. I think the one we did on Wednesday was 1 out of 250, if I recall. This hypothetical disease affects 1 out of 1,000 people, so fairly rare. And this time, our blood test correctly identifies the disease 99% of the time when the person actually has it. That's what I mean by correctly. Which is, I think, higher than the one we did on Wednesday. So that's a pretty good test, at least for detecting the disease. And it like most tests, there still would be some false positives. This time, it's only 2% of the cases when the person doesn't actually have the disease, they'll test positive with this test. So this is a much more, I would say, accurate test in both senses. Detecting it and falsely detecting it is a very low percentage. So pretty good test, right? But still, we want to find, so let's find the probability that a random person who gets this test tests positive. All right, and so be helpful to, don't have to write, test positive or has disease if we just denote. And you can do this either way. I'll use A. I think this pen's running out. Let's see. Green. I've got lots of green here. Let's see. So let's let A be the that the person has the disease. And B represent that the person tests positive. And of course, they either have the disease or they don't have the disease. So we could talk about A complement being no disease. And I know sometimes they, in examples, they'll go through all the options. Of course, I could call the complement of B representing that there's not a positive test, that it's a negative test, but we're not interested in that. We're interested in the tests, people who test positive. So I'm not going to worry about the negative tests here. And what we're looking for is the probability of B, the probability that somebody tests positive. And just like last time, we can see that we're going to get positive test results from people who, of course, have the disease, but also in a few cases, people who don't have the disease. So that's going to come from two groups, so to speak. And so I like to use the tree diagram because it really emphasizes that we got two different things contributing to that probability. You don't have to do this. I don't think I saw it in the notes in class, but it just helps me to visualize this. So first thing we want to first thing is consider the people who have the disease, which is 1 out of 1,000. Okay, this pen's. And then the probability that they test positive given that they have the disease, right? So this 99% is actually a conditional probability, isn't it? That's the positive test given that they have the disease. So that would be 0.99. And the probability that they don't have the disease, because those people are going to generate some positive test results, would be the complement of 1 over 1,000 is 999 over 1,000. And we multiply that by the probability that they test positive given that they don't have the disease, which is your 0.02. And maybe somebody can confirm. I think I have numbers here for this. Yeah, so you would multiply these together. If you multiply those together, that's a times here. You end up as a decimal. Well, it's 0.99 over 1,000, right? And as a decimal, that's 0.00099, right? It as expected is pretty small because not that many people have the disease, right? Only 1 out of 1,000 people have the disease. And likewise over here, this is 0.02 times 999 over 1,000. If you work that out as a decimal, well, here, I'll just write it again. And that comes out to be 0.02097. Nope, it doesn't. I lied. This comes out to be 0.1998. 0, put a 0 in front of there. And if you add these up, that becomes 0.02097. There we go. Okay, and so this you could interpret this as well. We probabilities can be written as decimals. They don't have to be converted to percents necessarily, but you could obviously see that that's just over a hair over 2% of people who take this test are going to test positive, right? But you can kind of see here, you know, in terms of who's contributing to that, most of that number is coming from the people who don't have the disease, right? And even though it's a very small false positive rate, 2%, but that's applying to the most of the people, right? 999 out of the 1,000 people are the ones who don't have the disease. So if you times that by 0.02, you can see why that's just a little bit under 0.02, because that's almost 1, right? So most of that number, this number right here of all your positive tests, are coming from people who don't have the disease. Okay. So here's the question. And we didn't ask this last time. I think last time I said, you know, I posed the question, if you're you're the doctor of one of these people, you know, what would you advise? Because they're going to be freaking out, right? They're going to be saying, oh no, what do I do now? And you're going to maybe try to convince them, yeah, well, let's take the test again. Remember that? On Wednesday, we said, well, let's try the test again and see what happens. But essentially, why are they worried? What they want to know from you is, now that they've tested positive, what is the actual probability that they have the disease, right? So this question we didn't ask last time. What's the probability they have the disease? And this is, in fact, a conditional probability, right? Because what we want here is the probability that they have the disease. Remember, A was the event of having the disease. So we want to find the probability that the person has the disease given that they've tested positive. This is what we want. Now, we did see back up here the opposite conditional probability, right? The probability that they test positive given that they have the disease. That was the 99%, right? So we actually want the opposite conditional probability than was essentially just given to us in the problem description. And so when this is an example where we're going to be using Bayes' theorem, Bayes' rule, which really is nothing more than, I don't have the notes from last time, but you may remember from a previous, I'll put from, was it? Sure, yeah, it must have been Wednesday. It was either Wednesday or Monday. From previous class, when we were talking about the probability of A intersect B, A and B happening, we decided that it could be either equal to the probability of A times the probability of B given A, or, in other words, that would be the same as the probability of B times the probability of A given B. Look back in your notes, right? That's how you find the probability of A intersect B. It's either this times this or this times this, depending on what order you have it in. And so what that means, this is the part you want to focus on. This is the part you want to focus on. Both of those equal this, which means both of these two things equal each other, right? These must be equal. And I always teach, when I'm teaching Bayes' theorem, just know this, because what'll happen is when you're trying to find a conditional probability that's not given in the problem, it's either going to be this one or this one. And you never know, depending on how we label the events, we never know which one we're going to be solving for. So in this case, based on the way I've defined my events, I want the probability of A given B, which is right here. So let's just isolate this probability. If I get this by itself, that means I'm going to divide both sides by B. So the probability of A given B, this one right here, is going to be equal to the probability of A times the probability of B given A divided by the probability of B. Okay, and because see, on another one, maybe on the next one, you actually want this one, in which case you would divide both sides by the probability of A, right? So that's why it's better to just know this right here. Okay, so I've got it right here. So this is our formula. This is how we're going to answer the problem. So the probability of A given B is the probability of A times the probability of A given B, B given A, sorry. And we actually have all of that information in the problem. If you go back up to your tree diagram, probability of A times the probability of B given A, we did that, right? These were the people who have the disease, huh? Probability of A times the probability of B given A. That was your 1 over 1,000 times 0.99. And the probability of B is the probability that a person tests positive, which was our whole answer, right? That's what we found in part A. That was both of these, right? So that is this 0.0297, 0.2097. If you don't get to use a calculator, you could just write out the sum of those two probabilities. And so this is it. And this comes out to be see this number right here, we had that number too. That was 0.0099, 0.00099, I should say, divided by 0.02097, which is approximately, thank you for answering that question. Yeah, it's Bayes' theorem, yeah. And it's really nothing more than just what we've already learned. It's just equating these two things here. You can call that Bayes rule or Bayes theorem. And I guess if you do this, that sounds about right. It's 0.047. Thank you for the calculation. So about a 4.7% chance that the person actually has the disease. Probability that the person has the disease. So pretty small, right? Not too high likelihood. And overall, what you can see, because I want you to think intuitively, I don't want you to rely on formulas. It totally makes sense. If we want to find the probability that the person has the disease, let me move this back up here. All the information's right here. It's basically just the ratio of this number, right? This was the positive test probabilities from people who actually had the disease. You would divide that by your total probability of positive tests, right? It's this over this. It makes sense. That's the fraction that we're looking for. Okay. And so just for practice here, let's continue with this problem, because you could tell that to your patient and they would say, thank you, doctor, that seems very low. Nevertheless, I'm still concerned, right? That's less than 5% chance I might have the disease, but I'm still concerned. I want to be sure if I don't have the disease, maybe I need to start treatment, or, more investigations to see what's going on, right? So as we posed last time, maybe what you would then still advise your patient to do is to take that test again. So let's calculate that probability. And maybe we'll call this, since we had B in the previous one, the probability that they test positive, let's call this the probability of 2B, testing positive twice. And just like the first one, testing positive twice in a row is going to come from two groups of people who actually have the disease and people who don't have the disease. And we went through this last time, but it was kind of at the end. The way this works then is we're assuming, I should have probably written this in here, assume test results, here we go, are independent. That was another topic that we discussed, and we're going to discuss more today because I saw that there's some questions about that on the homework. Okay, what does it mean for two things to be independent? From an intuitive level, it means that the fact that the person tested positive the first time, we're going to assume that has no effect on the probability that they test positive the second time, in which case, what that allows us to do for the probability of testing positive twice is to think of the probability they tested positive the first time was 99% if they had the disease, and the second time it is still 99%. That probability has not changed. So this would give me 1 over 1,000 times 0.99 squared. I'll work out that number, maybe somebody can. And then same thing down here, the probability that they test positive twice given that they don't have the disease is, what did I say it was, 2%? So 0.02 times 0.02. So that would give me 999 over 1,000 times 0.02 squared, which is approximately, and we're going to add these two. Yeah, so if you don't have a calculator, you just write this plus this and just leave it at that. But yeah, so it's not, so it's kind of like, that's a good question. Why can't we just multiply it by 2? You would actually have to square it because let's think of something else. Like if you flip a coin, the probability you get heads on the first flip is 1/2. Probability you get heads on the second flip is 1/2. If I wanted to find the probability that I got 2 heads, I would actually multiply those two together, right? It would be 1/4, because if I added them, that would get 1. That would give me 1. Or if I doubled it, right? If I doubled the probability 2 times 1/2, that wouldn't make sense. So you're going to multiply when you do these. Yeah. Okay, let's see. I think I have numbers for these two. This one up here is 0.000981. Didn't change very much. This one right here is, but this one changed quite a bit. 0.000396. So if you add these together, the probability of testing positive twice, summing these up gives me about 0.00138. Which you can see that's a pretty low probability for anybody to test positive twice, right? But then, so here's the question. So what if your patient was still tested positive twice, was in this very low probability of testing positive twice? Now you want to know what's the probability they actually have the disease. And just from an intuitive level, okay, the way we can answer this literally is to just say, of this total probability of positive tests, 2 positive tests, how much of that came from the people who actually had the disease? It's right here, huh? So it's literally going to be this fraction divided by this fraction is going to be our answer. Okay. Now we'll work out the formula too, but you can hopefully see here that this number is now a little more evenly split, isn't it? In fact, I can tell that more of this number comes from the people who have the disease now than people who don't have the disease, right? So you should probably be predicting here that it's a very much more likely situation that if your person tested positive twice, that they actually have the disease. But how we could write this out is, like we did last time, we could say, okay, we want the probability that they have the disease given that they tested positive twice. This is the probability that we want. And so off over to the side, what I would do is I would say the probability of here. Oh, okay. The probability of A times the probability of testing positive twice, given that they have the disease, should be the same as the probability of testing positive twice times the probability that they have the disease, given that they tested positive twice. Okay, in other words, the order, you just switch the order, right? This has to be true. And so the probability we're looking for here is now this one right here. This is what we're looking for. So I can isolate it by just taking this and dividing by the probability of 2b. So I would be thinking about this. And now I'm going to solve for that. So the probability that they have the disease, given that they've tested positive twice, would be this. Divided by the probability of 2b, which is, okay, go back up to all the information you have is in your tree diagram, except I realized I didn't write this part correctly. This was actually a conditional probability here, right? This should have been the probability of testing positive twice, given that they have the disease. So this top branch of our tree is the numerator. So this is your 1 out of 1,000 times 0.99 squared. And the denominator is your total probability of testing. That's what we just worked out. That is your 1 over 1,000 times 0.99 squared plus 999 over 1,000 times 0.02 squared. Or in other words, just 0.000981 divided by 0.000138, which is about I'm getting about 71%. 0.71, which can be interpreted now as a 71% chance that they have the disease, right? So that's much, much higher chance they have the disease. Okay. So yeah, I think this is like very, very important math, right, for the world of medicine and the idea of testing. Definitely if you're in the medical field, probability stuff you want to know. That's at least more interesting than pulling marbles out of urns and drawing cards, but we also have examples using this concept with those, so we should do a few of those too. So all right, so here's a similar kind of a thing, but phrased in terms of cards. So let's say we draw 2 cards from a deck of 52, and we want to find the probability that the first card was an ace, given that the second card was an ace. What's out here? So why don't we let A equal the event that the first card was an ace, and B represent that the second was an ace. So what do we want here? We want, it's a conditional probability here. We want the probability that the first card was an ace, the probability of A given that B happened, that the second card was an ace. Okay. And so anytime you've got a conditional probability that you're not sure, that's not given in the problem, this is when I want you to think of exactly what we've been doing here, that the probability of A times the probability of B given A has to equal the probability of B times the probability of A given B. And your conditional probability that you're trying to solve for will be in here, right? It's right there. So then the probability of A given B would be equal to the probability of A times the probability of B given A divided by the probability of B. Well, one of the characteristics of when you know you're using, so we'll refer to this as, to give credit, I guess, as Bayes' rule. Might look a little bit different, Bayes' theorem. One of the characteristics you know you're going to want to do this is when you're trying to find a probability from something that would have happened earlier, right? For example, like if you think about this, we're asking, we know that the second card was an ace, right? But we're actually trying to go back and figure out what was the probability that the first card was an ace, right? So you're going kind of back in time, right? If you think about the one that we just did, what we're trying to figure out is the probability the person has the disease after we know that they've tested positive twice. Do you see that's kind of similar? They would have had the disease or not, right, before, and then they took the test and got positive tests. So we're trying to go back and figure out the probability they have the disease. Does that make sense? That's the way I like to think of these, is that when you're trying to find the probability of something that would have happened earlier, right, then when my second card was an ace, I want to find the probability that something happened before that. Anyhow, so what do we know here? The probability of A is the probability that the first card was an ace. So that is, there's 4 aces in the deck out of 52. Times that by the probability that the second card is an ace, given that we've already drawn an ace, right? So this is a conditional probability. So how many aces would be left? We already drew one in the first one. So there would be 3 aces left, and there would only be 51 cards left in the deck. Okay, because we're not replacing these. I should have maybe indicated that clearly. It says draw 2 cards from a deck without replacement. I'm not putting them back in. Now that needs to be divided by the probability of B, which is the probability that your second card was an ace. And here's where it's not just this. It's not just this. Because remember, this 3/51 was the probability my second card was an ace under the assumption that I drew an ace on my first card. But there's another way your second card could be an ace, right? Your second card could have been an ace if you didn't draw an ace on the first card. So then what you have to realize is that this could happen right here. This could depend on whether I drew an ace first or not, right? Depends on whether first card was an ace or not. So you would need to like consider that. And then what are you thinking here? Well, what I'm seeing here is there's two situations where my second card could have been an ace. It depends whether my first card was an ace or it wasn't. So what I'm seeing here to answer this question is a tree diagram. If I want to find the probability my second card was an ace, I have to first consider my first draw, where my probability that the first card was an ace, we actually already did this. This is 4/52 times the probability my second card was an ace, given that I picked an ace, which is 3/51. But we also could have, I'll put or, if my first card wasn't an ace, and what would that probability be? There would be 48 cards in the deck that are not aces, and then times that by the probability that my second card was an ace, given that my first card was not an ace. Okay, so since we didn't take one of the aces here, I would still have 4 aces left in the deck, but I did draw a card, so I only have 51 cards left. So this is 4/52 times 3/51. And I want to add that to 48/52 times 4/51. And you end up getting a total probability of, I think some of these fractions can be reduced. Is it worth reducing it? I don't know. Yeah, so if you reduce this all, I mean, if you don't get a calculator on the test, I would just leave it like this, and I think that's fine. So what you could say is the probability of A given B, now that we know it's going to be this total sum here, is back up here. It's your numerator here, 4/52, 3/51. This is going to be our denominator, is the sum of those two. If you do a little bit of math with simplifying some of these fractions, what this ends up reducing to, surprisingly, you can reduce this whole mess down to 1/17. All right. So let's talk about, so this was a similar problem as the disease testing. The only difference was on the disease testing, I first, right, sometimes you get asked to first calculate the probability and then you get asked this. So you already have the tree diagram here. But sometimes you might just have to answer this conditional probability, and you have to realize that in order to calculate the probability of the denominator here, you have to, you know, consider the total probability. So I wanted to show you one of those examples. And, oh, of course, yes. All right. So there's been some talk about what it means for things to be independent, for events to be independent. And there's actually three ways you can show that two events are independent. One of them is that, you know, if A and B are independent events, then the probability of A given B, it shouldn't matter. B's occurrence should not affect A. So the probability of A given B should just be the probability of A. Same thing here. The probability of B given A should just be the probability of B. And what that would mean then is the probability of A and B would be the probability of A. Normally you would say times the probability of B given A. But if the probability of B given A is just the probability of B, it's just multiplying those two probabilities individually. So if A and B are individual events, all three of these have to be true, and we can prove that things are independent or not using any one of the three, although most of the time we'd be using this one. But so for example, if we flip a coin twice, and we look at the events that your first flip was heads, your second flip was heads, the question is, are A and B independent? In other words, does the fact that the first flip was a head influence the probability that the second flip is going to be a head? Your intuition is probably telling you, no, of course not, right? I like to say coins don't have memories, right? They don't remember what happened on the previous flip. So, but how can I really prove that to somebody? We could do this. I'm going to use this third definition. If I can show that the probability of A and B happening is equal to just the probability of A times the probability of B, then that would prove that the two events are independent. So to do that, I'm going to write my entire sample space, which would be, I got heads and heads. Maybe I got heads and tails, maybe tails, heads, or tails, tails. So the probability of A and B both happening, meaning the probability that I got heads on the first flip and the second flip, that's this 1/4, right? This is the one situation. This is your heads, heads, which is 1 out of 4. The probability of A is the probability that I got heads on the first flip and nothing more, right? You can't read any more into that I got heads on the first flip. Well, that would be, maybe I can color code this. Probability of A would be this one or this one, right? Those are the two events where I got heads on the first flip. So that would be 2 out of 4. And likewise, the probability that we got heads on the second flip would be both this one and this one, which is also 2 out of 4. And that's 1/2 times 1/2, which equals 1/4. So yes, right? Yes, they are independent. And then just to comment what I said before, you know, intuitively, we know that the first flip does not affect the probability of the second flip. So that's a pretty obvious one. All right, but now let's talk about one with, I don't know why they do this. This isn't just Professor Varn, this is our book. And even the old book did this thing for 17C. They like to talk about marbles in an urn or balls in an urn. I don't know about you, but when I think of an urn, I know an urn is like a jar. It is only 3 letters, so it doesn't. But when I think of an urn, I think, isn't that what, like when people put ashes, like cremation, they put them in an urn? It just paints the wrong picture for me. It's like, why don't we just use a jar? It just seems so. I know it's kind of strange. Yeah, it's very strange. Oh, which reminds me. Oh, okay. Little piece of Davis trivia. There was I don't know if anybody is familiar with this. Was a story that got some traction, but I think this happened in Davis several years ago. Was yes, Carrie. Did you hear the cookie story? Anybody know the cookie story? Okay, so apparently somebody got it in their head to take ashes and put them into cookies and bake them and pass them out to friends. And yes, it was kind of a weird story, but I don't know that much else about it. But yeah, I gather it was, but I don't know whatever became of it. But anyhow, let's get back to marbles. I just reminded me of that. So let's say you have let's call this a jar. Contains 4 red marbles and 6 green ones. We're going to pick out 2 marbles one at a time without replacement. That's key. And we want to find out the probability that the second marble is red. And then I'm going to have a follow-up question, because what we're going to want to determine is whether the events of picking a red marble first and a red marble second are independent events. Do I have time here? 9? Okay, yeah, I got time. We'll just finish this and then. Oh gosh. Oh, this is freaking me out. All right. Okay, so do you see what's going on here? Find the probability that the second marble is red. What you want to be thinking about here, we're picking 2 marbles and we're asked to find the probability that the second marble was red. How many people see 2 situations where the second marble could be red? Does that make sense? Two different scenarios of picking 2 marbles where the second marble was red. You see what I'm getting at? Because what this depends on is whether my first marble was red or whether it was green. I could get the second marble being red in both cases, so I have to break this up. So maybe instead of A and B, I could just use R and G, I guess, for red. And so probability, well, no, I guess I can't. Well, here's what I'll do. Probability that the second marble is red. Second, I better put second, or that's going to look like 2 red, that I got 2 red marbles. The second marble was red. Depends on whether my first was red. And what would that probability be? Well, there were 4 red marbles out of 10 in the jar. So that would be 4 out of 10. And then the probability that my second is red, given that my first was red. Since I selected a red marble on my first draw, whoops, then that numerator should be 3. And there would only be 9 marbles left in the jar because we're not replacing them. So this is going to come out to be 4/10 times 3/9. But we could also have the first not being red. I'm just going to put the first green, which is not red, which is, how many were there? There's 6 out of 10. And times that by the probability that my second was red, given that the first was green. So now I still have all 4 of my red marbles, but again, I took a marble, so I'd only have 9 left. So this ends up being 6 out of 10 times 4/9. If I add these together, so this is, let's just not worry about simplifying the denominator. This is 12 out of 90 plus 24 out of 90. So if I add these together, the probability that my second marble was red is 36 out of 90. I guess I can reduce that because 9 goes into both of those. So that is 4/10, which reduces to 2/5. And then let's just answer this question and we'll finish up. So are the events of picking a red marble first and picking a red marble second, are they independent events? So let's think about this from an intuitive level first, right? What that's basically asking is, does the event of picking a red marble first influence the probability of picking a red marble second? What do you think? Yes or no? Yeah, how many people agree that definitely influences it, right? Because I've taken out one of the red marbles, so that's going to change my probability. So yes, these should not be independent events. So how we can show that is to show, we want to show if the probability of picking my first marble red and my second one red, does that equal the probability of my first one being red times my probability of my second one being red? I'll put a question mark. Well, this probability right here, we can just run through. The probability that the first one is red is what was it? 4. There were 4 of those, 4 out of 10 times the probability the second is red. Now both of these happen, right? The first one's red and the second one was red, so this would be 3/9. The probability that the first one is red is also 4/10 over here. But here's the thing. Over here, these things would have happened together, right? We're trying to find that this happened and this happened. So we have to consider the fact that we picked a red first. But when you're doing this, this is its own probability. In other words, this should be the total probability of picking my second marble red, not including it doesn't matter what happened first, just what's the probability that my second marble was red. And that is exactly what we just worked out. The probability that the second marble was red came out to be 2/5 or 4/10. In fact, why don't I use, well, yeah, it doesn't matter. I'll just use 2/5. This one we worked out to be 2/5. And let's see, this comes out to be 12 out of 90. Right now, if I multiply those together, that is 8 out of 50. If I can reduce this down, 3 goes into this, 4 over 30, 2 goes into that. That's 2/15 in its simplest form. Here, let's see, 2 goes into that 4 times. 4 out of 20. I think the best I can do to reduce this is 4/25. And clearly these are not equal fractions, huh? These are not the same. So these two events are not independent. Not A and B, not independent, as kind of expected. Yeah. Okay, so hopefully this helps your homework, and I guess we have just one more meeting on next Wednesday. I hope you all enjoy your 3-day weekend, get some rest, get some outside time, but also I'm sure many of you use this time too. You got, we get back, we've got 1.5 weeks till the end, so make sure you get done what needs to get done.